distribution. So you can use that even for your own paper, okay, if you want to test for unit root. Okay, now let's go through the different cases. So there are basically 3 models that we'll consider, okay, but I hope you understand this. So, and that is the biggest issue here regarding, I mean, one of the biggest issues regarding integrated processes. So there are 3 models that are considered. So I'm going to start with model 3 because this is how it's done in the literature. So I'm not, I don't know why they didn't use model 1 here for that one, but this is basically what you would have. So I'm looking at both sides here of the tech. So you have basically the first regression, okay? So the first regression is, okay, again, yt is, I mean, as I just was introducing here to it, so yt minus 1 plus the noise. And the second regression is basically equivalent to that, which is about, regressing the differences here of the process on the previous observations here. Okay, so which is going to be the same. So again, these 2 are equivalent. Okay, so please note that, of course, rho minus 1 is going to be equal to phi here for that parameter. So the 2 are equivalent, but I'm looking at both sides here of the tail anyway. Okay, now the so-called knot hypothesis. Okay, so the knot hypothesis. Okay. Okay, so here for the first model is obviously, as we have seen before, the knot hypothesis is that that basically rho is equal to 1. Okay, and for the second model, again, the 2 both are equivalent. The knot hypothesis is that phi is equal to 0. Again, so this is equivalent because rho minus 1 is equal to phi. So if rho is equal to 1, then phi is equal to 0, and if phi is equal to 0, then rho is equal to 1, obviously. Okay? And this means that if these things are true, then basically you will have that y, okay, so this suggests, okay, the knot hypothesis suggests that basically y has a unit root with 0 drift, okay, so this is y has a unit root with 0 drift, okay, so unit root process with a 0 drift, okay, because, I mean, here in this case, if phi, let's say you can see this clearly, if phi is equal to 0, then of course the difference will be stationary, and the difference of the process is stationary, and of course the original process which you would get by summing it up is going to be integrated according to right to 0 drift. Of course, there will be no drift here. Okay, so this is what the knot hypothesis says. What is the alternative? Okay, what do the alternative hypothesis say? So in the first model we already talked about it. The alternative hypothesis is that the absolute value of the process is going to be less than 1. Again, we'll exclude the case where the absolute value of the process is greater than 1, because in that case the process will tend to infinity anyway, so why would you consider that? Alright? So this is not what you need to look at. Okay, so this is the knot hypothesis, and these are the alternative models. These are the alternative hypotheses here for the 2 models. Okay, so for the second model, the alternative hypothesis is, and this is more common, that you'll have that phi is less than 0. Okay, so again, I think that the second model is more intuitive than the first one, but this is just my personal opinion, guys. Okay, so you can see. I mean, you can find sense of that. Now, here in this case, if let's say rho is going to be less than 1, maybe remember this here from this representation. If rho is less than 1, then the process is stationary, and the mean of the process was equal to the constant divided by 1 minus a. Remember. Okay, so let me just add here this to it. So if let's say yt was an autoregressive process, okay, so we have a constant plus a times yt minus 1, okay, plus the noise, and let's say the process is stationary, then the expectation here of the process was equal to the constant over 1 minus a. Maybe remember this. Now here you don't have any constants here in this case. So if you don't have a constant, then basically the expectation would be 0. Okay? You don't need to write it down because that is something here from the previous chapter. Again? So that was the expectation here for that. Okay? So in this case, v divided by 1 minus a, if v is equal to 0, then the expectation is 0. So in this case, the alternative hypothesis suggests, okay, that that basically y is stationary, okay, with a 0 mean. All right. So this is what you would basically you would get as a result. Okay. So this is what the alternative hypothesis say. Okay. Now, if let's say, and this is what you have as a distribution. Okay. So the distribution of the test statistics under the not hypothesis. Okay. So if the not hypothesis is true, this is what it says. Okay. Then the test statistic rho, which is of course equal to the test statistic phi, which I introduced here before, will both converge towards the so-called Dickey-Fuller distribution. Okay, so dF denotes Dickey-Fuller distribution. Okay, Dickey-Fuller distribution. Okay, so this is a special distribution again, which is, I mean, no, it's not similar to the normal distribution. If you take the standard normal distribution and shift it to the left, then you're going to get something like that. Okay, so the shifted normal distribution will be the Dickey-Fuller distribution if you use the critical values here for that. Okay, I will provide critical values here for that distribution as well. Okay, so this will be, okay, that will be another issue. I have provided critical values here for the standard normal distribution, for the t distribution, for the chi-square distribution, etc., and I will also add that the Dickey-Fuller distribution as well. Okay, so then you're going to see, I mean, this will be more or less accurate. So then you're going to see whether or not your assignment is fulfilled or not. Okay, you're going to get some deviations, of course, because due to the simulation, right? So each and every one of you will have different critical values. Okay, but they will more or less, more or less be the same depending on the number of repetitions that you use for your simulation. Anyway, okay, so this is the so-called distribution. So, and you will reject the null hypothesis. Okay. You can reject the null hypothesis, okay, if basically the test statistic, so any of the test statistic, okay, so I take the first one, let's say, is less than the alpha quantile, okay, so of the Dickey-Fuller distribution, okay, so this is the alpha quantile. Okay, so this is the alpha quantile of the Dickey-Fuller distribution. Okay, of the Dickey-Fuller distribution. Okay, that's it. Okay, so we reject the null hypothesis at level alpha. Okay, obviously. Okay. And alpha will be the error probability that you choose. Okay, so alpha is the error probability. Okay, so that was the first model, and we already talked about it. Okay, So there is also a second one where you have a constant. So in this case, it's going to be something else, okay? So you have a constant here in the model, okay, because here in this case you don't. So that will be, this is model 3, and the next one will be model 2, okay? So in model 2, you're going to have a constant here as well, okay? So you can choose either from the following regressions, so the first one here and the second one. Okay, so the first regression is you have yt and then you have a constant m plus rho times yt minus 1 plus the noise. Okay, so that's basically your first regression. Again, so here for instance, if rho is equal to 1, then you're going to get, a process with a unit root, of course. Okay, and the second part, which is equivalent here to that, is going to be that you have m plus phi, okay, times yt minus 1 plus the noise. And here you have to be careful, okay, so I mean, because of course you have the same thing, so phi is equal to, and then you have rho minus 1, okay, but I'm using a reparametrization for the constant as well. So the constant will be equal to, and this is what you're going to have, 1 minus rho times mu, and mu is a constant. So basically what you have is rho, if rho is equal to 1, then the constant will be also 0. This is just a reparametrization that we use here. Okay, so basically the real constant is going to be 1 minus rho times mu. This is just a reparametrization here of the process, so in order just to have basically one hypothesis regarding just one parameter. Okay, so if rho is equal to 1, then basically that the constant will be equal to 0. Okay, and if rho is not equal to 1, then the constant will be not 0. That's it. Okay, so here in this case, I mean the knot and the alternative hypotheses are the same, so let me just make that short. Okay, so the hypotheses are going to be as follows. Okay, so for the first model, you'll have that the knot hypothesis is going to be equal to, I mean, we'll say that basically that rho is equal to 1, meaning that the process has a unit root, and the alternative will be that the absolute value of rho is less than 1, and for the second model, you'll have that the knot hypothesis says that phi is equal to 0, meaning that the process will have a unit root. Okay, so if phi is equal to 0, then of course you'll have that the constant here will be also equal to 0. Okay, and the alternative hypothesis will say that phi will be less than 0, which is of course equivalent to the alternative hypothesis here of the second model, of the first case. Now, of course, here in this case, the knot hypothesis suggests, okay, the same, okay, that basically that the process has a unit root, okay, with the 0 drift, okay. So that's going to be the same. And the alternative hypothesis suggests, okay, that in this case, and you just look at that. So if the alternative hypothesis is true, then of course the process here will be stationary, and the mean will not be 0, okay, because the constant is not 0 if the alternative hypothesis is true. So if the alternative hypothesis is true, then you're going to get a stationary process with a non-zero mean. That's the difference here of model 3 and model 2. So here you have that here in the alternative hypothesis, just the stationary with a 0 mean. And in this case, if you include a constant, the mean will not be equal to 0, obviously. So that's the only difference. Okay? So here in this case, it will, okay, so the alternative hypothesis would suggest that y is stationary with a non-zero mean, okay? So the mean will not be equal to 0. So depending on which model you choose, okay, we have to figure out from the perspective of economics which model does make sense, okay? So if you choose model 3 as your basically your testing result, then you have to make sure that if you reject the null hypothesis, that the mean evolves around 0. So for instance, for interest rates, that's not going to be true, okay? So if you look at, for instance, interest rate processes, the interest rate process, if it's stationary, it doesn't evolve around the 0 mean, guys, okay? Because then in that case, you would have cases where the interest rate is positive, and you would have that the interest rate is negative. Now, of course, there are such things as negative interest rates, but I'm not suggesting that basically the mean of the interest rate is 0, so it's not going to be the case. Okay, so if you, let's say, for instance, test for interest rates, okay, you will figure out whether the interest rate process has a unit root or not, then you would basically take model 2 instead of model 3, okay, because the mean of the process would not be 0, okay, all right, okay, but as I said before, whether you take model 3 or model 2 depends on the content, okay? So model 3, for instance, does not make any sense if you, let's say, if you test that for interest rate processes, again, because in that case, if the null hypothesis is rejected, you would assume, or model 3 assumes basically, that the process is stationary with a 0 mean, okay? So, and that's obviously not the case, okay, from the empirical perspective, okay? So that's what you're gonna, when you look at, you'll have to look at what the alternative hypothesis say, okay? And here it says it's stationary with a non-zero mean, okay? So here, in the first case, it was stationary with the 0 mean, and in the second case, and model 2, it's stationary with a non-zero mean, okay? Now, the principle is similar, so you reject the null hypothesis if basically, and this is what you would do, similar to the previous section, okay, so we reject the null hypothesis at level alpha, okay, so at error probability alpha, if the test statistic here, okay, which is basically equal to the other test statistic, is less than the Dickey-Fuller distribution, okay, or the alpha quantile here of the Dickey-Fuller distribution. Now I will add the constant here, so because this is a modified, okay, so if you have the constant mu, which refers to the constant here for the model, which will be, of course, the mean here of the process, then we're going to get basically that this is a modified Dickey-Fuller distribution. So here you're going to even get other critical values. Okay, so this is also a modified Dickey-Fuller distribution. Okay, or basically this is the alpha quantile of the modified Dickey-Fuller distribution. All right. So there are two. I mean, there will be 3 versions depending on the model that you choose, okay? And the final model, which is basically model 1, okay? This is what the first model will be about, okay? So this is the model 1. This is the most general one, okay? So here, this is going to be, the first model was like this, okay? So we have rho times yt plus et. I mean, the first model that I introduced, but that was model 3, okay? Now model 2 basically involves a constant here. So the constant plus basically that part. And model 3 involves also a linear trend, okay? So here you're going to get also a linear trend. This is what you have, okay? So here in this case, you'll have d times t. Again, so and d times t is a linear trend. Let me just write it more clearly so you see it better. So d times t, this is a linear trend, okay? And then plus rho times yt minus 1 plus the noise. And the second model will be that basically you have delta yt, okay? It's going to be the same thing except for phi, okay? So m plus dt plus, okay, phi times yt minus 1 plus the noise. Again, here you also have that rho is equal to phi plus 1, okay, or 1 minus rho is equal to phi anyway. And you're also going to have a reparametrization here of the coefficients, so you only need to have just one statement here regarding one issue. So the constant will be, again, so this will be the same thing, so this will be 1 minus rho times mu plus rho times delta, okay? And delta is going to be also another parameter, and you have the parameter d, which can be also represented by means of 1 minus rho times delta, okay? So we use these reparametrizations in order to make sure that if rho is equal to 1, here for this case, if rho is equal to 1, then the constant will be 0, you see, m will be 0, and also the linear trend will be also 0. You understand this? So again, just please focus on rho, okay? If rho is equal to 1, then m will be 0 and d will be 0, okay? So there will be no linear trend and no constant here. Okay, so that that involves basically that the same null hypothesis, that the null hypothesis suggests that y has a root with drift rho basically, but this is going to be, this is what you would get. So the alternative hypothesis, and let me just illustrate this. So these are going to be the hypotheses. Okay, so this is what you would get. Okay, so the first one is that the null hypothesis states that rho is equal to 1 here, or basically here for the second model, and the alternative is that the absolute value of rho is less than 1, and the second basically claims that, okay, so for the second model is that phi is equal to 0, where basically the alternative hypothesis is that phi is less than 0, okay? And here the alternative hypothesis suggests that the process is transstationary again, okay? So if the alternative hypothesis is true, then the process will be transstationary, obviously, okay? So that's why you would, okay, so the alternative suggests that y is transstationary, okay? So stationary around the linear trend, okay, so around the linear trend m plus d times t. So this is the trend that you will get, okay? So if the null hypothesis is rejected, okay? So these are the three cases that you distinguish, all right? So either, the question is which case you would take, and the answer is relatively simple. It depends on what you would assume if you reject the null hypothesis. For instance, interest rates are relatively constant, okay? So they are stationary, but not with the zero mean. So for interest rates, let's say you would use model 2, okay? But for instance, stock returns, okay, or stock prices whatsoever, there is a linear trend here, for instance, in the stock prices. So according to, let's say, for instance, the Black-Scholes model, okay? So yeah, then you would basically choose model 1 for that. So depending on basically how the time series would look, Okay, so the first thing that you basically do is you look at the time series and you see whether or not, you know, the alternative hypothesis of model 1, model 2, or model 3 basically holds. Okay, and then you choose your model according to that. All right, so here in this case, and just 1 minute, guys, so, and that will be the final case, so reject null hypothesis, okay, at level alpha, okay, if basically the test statistic, which is equal to the test statistic here for the other model, okay, is less than the second modified Dickey-Fuller distribution. Okay, so this is going to be another modified version here of the Dickey-Fuller distribution. Okay, so I'm using tau here to distinguish here for that. So the Dickey-Fuller distribution for a linear trend in the time series. Okay, so this is the second modified. Okay, so the second modified Dickey-Fuller distribution. Okay. So where you basically have a linear trend in a data. Okay. So we just for a linear trend in the data. So that's that will result in a different distribution as well. Okay. So that will be basically your assignment. Okay. So you are allowed to choose any of the 3 models you like. I mean, the easiest one is going to be the first one, obviously, but you can also choose the others. It's up to you. Okay, so according to that grid parameterization, so you can include a constant or linear trend whatsoever, and you simulate the data, you look at the test statistics, you assume that the null hypothesis is true, so you simulate integrated processes, then you look at the empirical distribution of the corresponding test statistics that you will get from the simulations, and based on the empirical distribution of the test statistics that you will get from the simulations, you basically establish the critical values of the Dickey-Fuller distribution. That's going to be it. Okay, so that's going to be basically your third and final assignment. Okay? Now, next week we don't have any lectures, but I would like to talk to you instead, so please make sure that you find the corresponding time or corresponding date, okay? And where you have a little time just to talk to me about your seminar work, okay? Because I'm going to address certain issues regarding your paper, so I think it's easier for you to if you talk to me one-on-one regarding this issue. Okay? So, and I repeat, but your third and final assignment will be just about that, and I will evaluate your assignments during Christmas and New Year's. Okay? And then so you'll get them until then. All right? Okay? Okay, guys, so please send me an email, let me know when you have time next week, so to talk to me, okay?